Hello DSC 20 students, my name is Carter and today we are going over complexity. First, we'll go over the definition of complexity, the difference between time and space complexity, and the complexity notation that we'll be using in this class. Then I'll demonstrate why we need complexity through a classic example of the Fibonacci sequence. It may be hard to understand the difference between different complexities across small and large values of n, so I'll be visualizing common complexities to graphically explain the differences between them. We'll finish up by going over common occurrences in complexity problems, organized by complexity. Now, to get to our topic for today, let's talk about the definition of complexity. Formally, complexity is the measure of the amount of computing resources that a particular algorithm consumes when it runs. There are two main types of complexity, time and space complexity. As you can probably infer, time complexity refers to the amount of time an algorithm takes to run, and space complexity refers to the amount of memory the algorithm takes to run. Often you'll see complexity notation using big O, which is capital O of n. More formally, the complexity that we'll be referring to in DSC 20 is actually big theta, which uses the Greek letter theta to refer to the average case complexity, rather than the worst case complexity of big O. So, to demonstrate why we need complexity, here's an example you all should be familiar with, the Fibonacci sequence. The Fibonacci sequence is computed by taking the sum of the two previous Fibonacci numbers, starting with 0 and 1. For the sake of this demonstration, we'll use 0 indexing, so the 0th index Fibonacci number will be 0, and the first index Fibonacci number will be 1. So to get the second Fibonacci number, we would first calculate the 0th and first Fibonacci numbers, and then take the sum. As you can see, we already have 0 and 1 as their respective Fibonacci numbers, so the second Fibonacci number will be 0 plus 1, or 1. The next will be 1 plus 1 equals 2, and then 1 plus 2 equals 3, and so on and so forth. Now, what if we want to make a function to calculate the nth Fibonacci number? One solution would be something along the lines of fib recursive, which follows the recursive process that we just outlined to calculate the nth Fibonacci number. We have our base case for the 0th and first index, and then any Fibonacci number from 2 onwards would be calculated by the sum of the previous 2 index Fibonacci numbers. As you can probably see, this implementation is not very efficient. Calculating the 4th Fibonacci number would call the function to calculate the 2nd and 3rd Fibonacci number, and to calculate the 3rd Fibonacci number, we would call the function to calculate the 2nd Fibonacci number again. With the picture of the recursive calls visualization, you can see places where our algorithm will make repetitive function calls. Each circle is a function call. Look at how many times our recursive function is called to calculate only the 5th Fibonacci number. Our next implementation, fib_iterative1, uses a list to store the current sequence. With this approach, we can tangibly see the trade-off between using more memory to store the computed numbers and using more computation with more function calls. A more efficient way for calculating a single Fibonacci number would be to use temporary variables so we don't have to keep track of the entire previous sequence. Fib_iterative2 only keeps track of 2 numbers, a and b, in order to save memory. For our final Fibonacci function, we will use linear algebra and matrices to approximate the nth Fibonacci number. If you want to learn more about the proof and methodology behind this approach, you can visit this blog post. So now that we have all these different ways of calculating the Fibonacci numbers, how can we quantify which approach is best? Right now we'll just focus on which function is the fastest, because it should be relatively easier to methodically compare. One way we can compare the run times of each function is to time the time each function takes to calculate the same Fibonacci number, and then compare the times between the functions. Let's see which function is the fastest at computing the 30th Fibonacci number. As expected, the naive implementation is by far the slowest. It seems like an iterative approach worked best on our test run. Now, what if we use the average of 10 runs in order to be more robust? Here it looks like the list version could be faster than before. Note the list is not being reset in between runs, so that could definitely be an influencing factor in these results. By keeping n the same between runs, the list version just has to access the previously calculated value, which obviously takes much less time than other methods. How about comparing the functions at runtimes as n, the input size changes? Well, let's plot it. I'm going to remove the recursive function because we already know that it's the slowest and it will take a lot longer to generate the plot if I include it. You can see various spikes across each of the functions, and it's hard to tell which function is performing best across any of the values of n. As you can tell, this approach is not a great way to assess how efficient an algorithm is. Additionally, if we ran this on a computer other than my MacBook, we would get different results. Since I'm recording this video, there are also background processes that could be creating noise in our data. Hence, we need complexity to compare our algorithm's running time and memory usage independent of the testing machine and any other confounding variables. Now that we know what complexity is and an example of why we need it, let's visualize some common orders of growth. I'm going to visualize O of 1, or constant time, O of log n, logarithmic time, O of n, linear time, O of n log n, linearithm, O of a to the n, exponential, O of n squared, quadratic, O of n to the k, polynomial, and O of n factorial. Constant time, or O of 1, is just a horizontal line. Constant time stays constant as n increases. Logarithmic time increases, but it levels off and starts to look more like a horizontal line as n gets closer to positive infinity. Linear time increases at a constant rate. Linearithm, n log n time, is a mix of linear and logarithmic time. I remember the difference between linearitmic time as a relationship between log n and 1. When log n is less than 1, or for smaller values of n, linearitmic time is less than linear time. When log n passes 1, or for larger values of n, linearitmic time grows greater than linear time. Here we have exponential time, which could be any positive number to the nth power. Think of compounding interest or bacteria growth. Quadratic time and polynomial time are similar, where k equals 2 for quadratic, and in polynomial time k can be any positive number. Hopefully these graphs helped you all visually understand the difference between complexities. Now let's go over some problems. Let's say we have our n value. Here we'll take the randomly generated value 193. Here are some examples of constant time complexity problems. We have addition and multiplication. Any arithmetic operators will be evaluated in constant time. Print statements also run in constant time. Now here's a tricky one. We have range n, which you would think would be in linear time. Range is actually an iterable, which means that range is evaluated lazily. We consider range as constant time until you actually iterate over it. The same goes for map and filter. Map and filter are both iterators, which means that they will both be lazily evaluated in constant time unless iterated upon or casted to a list. Here we have a function that, although it's looping over range n, has a return statement which would return n in the first iteration of the for loop. Therefore, it would also be in constant time because no matter how big n is, the function will always return after the first iteration. Onto logarithmic time. This code cell will loop log base 2 of n times. A telltale hint of logarithmic time is when we are multiplying or dividing an iterating variable by a constant. You can think of the constant as the base of the logarithm. We can also go the other way around. We can now start at 1 and then multiply by a value until it gets to n. For linear time, we have range again, but this time we cast it to a list, which means it will actually go through all the values of n, making it theta of n time complexity. With this for loop, it goes from 15 to 2 times n plus 30. We can ignore the constants and the lower order constant time by the properties of orders of growth, and then we can just see it as theta of n. Finding the max of a list or a set of values takes theta of n time because we have to look through each and every value. Likewise, the minimum also takes theta of n time. So max and min are then both linear time complexity. Next, we have nested while loops. The first loop condition depends on I, so let's look at the inner loop to determine the time complexity. With j equals 1 and j decrementing once every iteration of the inner loop will take 2n iterations until j equals negative I, which is negative n. 2n iterations means the inner loop is theta of n linear time complexity. Since the outer loop while loop breaks after a complete loop through the inner loop, the total time complexity is 1 times 2n, or theta of n. For theta of n log n time complexity, the first thing I think of is sorting. The default Python sorting algorithm runs in linear arithmetic time. You don't have to know the actual implementation of the sorting algorithm for DSC 20, but for DSC 30 you'll learn more about it. Just know that whenever you see Python's .sort, then that will be n log n. Next, we have another example of linear arithmetic time, where we start with an empty list, I equals 1, and then we go from n to 2n and append a value each time. Executing the append statement takes constant time, and the inner loop is from n to 2n, so n iterations, or theta of n. The outer loop is the classic I times equals 2, which is logarithmic. Combining the nested loops will give us n times log n iterations, which is theta of n log n. For exponential time, we have previously introduced recursive Fibonacci function. The time complexity of this function will be 2 to the n because every level will have 2 recursive calls, and there are n levels. You can refer back to the recursive tree if you want to see that. For quadratic time, we have this important formula where the sum from 1 to n is theta of n squared. This nested for loop is simply the above formula. The outer loop is from 1 to n plus 1, and the inner loop will run I times. In the first iteration of the outer loop, the inner loop will run 1 time. The next iteration will be 2 times, and it will continue until the inner loop runs n times. Next is another similar nested loop. The outer loop will be theta of n because 3 times n is the same as theta of n. The inner loop will also be linear time with respect to j. Hence, we have a nested linear time which is quadratic. For the last quadratic time example, we have a function that computes the max of a list inefficiently by computing the max of sublists. For each of the n sublists, it would take I iterations to calculate the max of the sublist, and the final return statement would take n iterations to calculate the max of the maxes. The for loop would take n iterations, and each inner max statement would be from 1 to n iterations, making the total loop theta of n squared. The final return statement with max would be theta of n, which would be dropped when ignoring lower order growth, making the overall function theta of n squared. Lastly, we have factorial time. Here we have a function that recursively generates the permutations of a list of elements. In this example, we have 6 options for the first letter of each permutation. It can be C, A, R, T, E, or R. Each successive letter will have one less option as the letters are chosen and fixed in place. That's all for now. Please let me know if you have any questions. I hope that this video was helpful in understanding complexity, and that you are better able to solve complexity problems with the examples I gave. Thank you for watching.